Okay, as Brian mentioned, our goals today, we're going to talk about, give you some background on streamflow duration. We're going to talk about what kind of characteristics we use to talk about streamflow. We'll describe what streamflow duration assessment methods are and how they're used. We'll discuss the streamflow duration classes this method is intended to help people determine. We'll then discuss how we developed the method for the Western Mountains, and then we'll finally give you a description of what that method actually is and how it compares to the arid West. If you're not speaking, please put your microphone on mute. Okay. So streamflow is defined simply as movement of water in a channel. This is different from standing surface water, subsurface flow or hyporheic flow or seepage. And also we are talking strictly about freshwater systems, so it's not movement in a tidal channel either. And there are many characteristics of stream flow that ecologists and hydrologists will focus on, things like magnitude of flows or the timing of flows. And we're really focused on the duration of stream flow. And we believe this is one of the most important aspects in terms of what it means for ecology and ecosystem functions. And it has a lot of management relevance, as many of you guys already understand. As you know, stream flow duration exists on a continuum of what we call wetter streams or perennial to drier streams, what we sometimes call ephemeral or episodic. But it is a continuum with a lot of gray areas in between. And we like to put classifications on this continuum. Some of the most widely used ones among researchers and within the management community are the terms perennial, intermittent, and ephemeral. And I just want to point out that even within this gradation, there's a lot of different ways to characterize how these streams differ from each other. You can talk about number of days of flow. You can talk about the predictability of when that flow occurs or the timing of that flow. So there's a lot of complexity to stream flow duration. So inherently, we have to simplify things to create a classification system in order to study and manage these systems. Streamflow duration is itself dictated by changes in the water entering or exiting a reach. The inputs come from discharge from upstream as well as discharge from groundwater, direct rainfall, or runoff from surrounding uplands. So all these things add water to the reach. The water leaves the reach by flowing downstream, percolating into groundwater, or evaporating, either mediated by plants or just through temperature. And the balance of the inputs and outputs determines whether you have stream flow present. And in ephemeral streams, in general, the outputs are stronger than the inputs, whereas it's the opposite in perennial reaches. And in intermittent streams, it depends on the time of year, really, which ones are the more dominant. So what is an SM, a stream flow duration assessment method? So the definition we use, it's a rapid, field-based method of classifying the flow duration of a stream's reach. Field-based, we mean that we're talking about indicators that we observe in the field. These are distinct from hydrologic models, which are another tool that can help managers understand stream flow duration, but they are not field-based methods. And they're rapid, meaning that they can be completed in a single site visit. You don't have to conduct long-term data collection in order to use them. What are indicators? So an indicator is it's an easy to measure property of an ecosystem that tells you something about a hard to measure property. So the hard to measure property is stream flow duration. The easy to measure things may include geomorphological characteristics, hydrology, biological characteristics, and geospatial measures as well, things like climate. Now, an indicator for a streamflow duration can be a control on streamflow duration. Basically, you're measuring something that actually dictates how much water is in the creek or how much water can leave the creek. For example, stream bed substrate composition can tell you something about percolation to groundwater. It can reflect responses to streamflow duration. Things like, you have biological organisms adapted to certain flows, like hydrophytic plants. But there's a third category that we didn't discuss as much during the Arid West method that is more relevant now. And these are factors that are associated with stream flow duration. They're not controls or responses, at least not in a strong or obvious sense, but are clearly associated with stream flow duration. So a good example might be sinuosity, where you have more sinuous streams, where you have more flows, even though it's not directly governed by that. In general, we prefer indicators that reflect long-term conditions over those that are more transient or reflect only recent conditions, which is why our SDAMs often feature things like biological indicators over things like the presence of water. So why do we need SDAMs? Like we mentioned, stream flow duration, it's one of the most ecologically important characteristics of a stream. And because of that, it underpins a lot of our regulatory and management programs. Notably, it helps us determine jurisdiction of the Clean Water Act, or Waters of the US, or WOTUS. The problem is that to really understand stream flow duration, you need long-term hydrologic data, and we are typically only collecting this at small numbers of sites, like USGS stream gauges, so we don't have the information where we're often making our management decisions. So having a rapid field-based SDAM will help us make the right decisions for those types of streams. So I want to clarify that stream flow duration by itself is not the same thing as a jurisdictional determination. Jurisdictional determinations are based on current regulatory guidance and policy, which may change as administrations have different priorities. Jurisdictional determinations for certain aquatic resources, that you need timely stream flow duration information, and that's what SDAMs are intended to provide. You cannot make the determination solely based on an SDAM. You need to consider a number of other factors, so it's really part of the determination. And most importantly, SDAMs have a number of other management and research applications unrelated to jurisdictional determinations. You can use them, for example, to help set restoration goals or to assess water quality. So there are a variety of applications beyond jurisdictional determinations. I would like to highlight what SDAMs cannot do. They can't tell you what the historic stream flow duration at a site used to be. They basically are only going to tell you something about present day or at least recent conditions. And more importantly, they don't tell you what conditions should be at a reach. That is a policy determination. And to sort of highlight this, I'm showing an example of a river in Arizona where it was historically ephemeral, but it is now has treated effluent sustaining flows, and this is done for the intention of both environmental and recreational benefits. So that's a policy determination. It's not an SDAM would not tell you that that's what you're supposed to do at a reach or not. We designed this SDAM to classify reaches into 3 categories, just like we did for the Arid West. Those classes are perennial, intermittent, and ephemeral, and these are some examples of our study reaches from our efforts to develop this method. Perennial reaches have, like I mentioned earlier, have inputs that are greater than the outputs of water in the reach. They contain flowing water throughout a normal year, and they typically have the stream bed located above the water table for most of the year. They may occasionally dry, but these are usually only in response to extreme climatic variation. Groundwater typically supplies the base flow for these perennial reaches, but there can also be stormwater runoff and snowmelt. This photo shows you Shell Creek, which is located near a USGS gauge in Wyoming. And that plot is a hydrograph showing the variation in stream flow from 1960 to about 2020, so almost 60 years. Those black lines show that the discharge can vary quite a bit throughout that time period, within a year and across years, but it never actually hits zero. The black line indicates some sort of positive discharge was measured at that stream gauge, so it was never dry over that nearly 60-year period. Intermittent streams, these are channels that have flow for only part of the year, typically during the wet season, and the stream bed is below the water table, or you have snowmelt sustaining it from uplands. They typically do have groundwater influence, but the flow varies greatly with stormwater runoff. The image on the right, this is Ward Creek, which is near Lake Tahoe in California. And again, it's a gauged stream. And again, you see quite a bit of variation in flow over that time period. It's a little short, it's about 45 years. Those red dots you see on that graph are times when the gauge recorded zero discharge. So you can see that the stream may not dry up every year, but it does dry up with some regularity, particularly during extended dry periods like you had in the past decade. Finally, we have ephemeral streams. Ephemeral reaches, they only flow in direct response to precipitation. They typically flow for only short periods and typically only after a large precipitation event. The stream bed is always above the water table, and stormwater runoff is the primary water source. That image on the right, this is Calf Creek from Northern California. And within the Western Mountains, we actually don't have USGS gauges deployed at reaches we found to be ephemeral. So instead, I'm showing you some data that we collected as part of the study using what's known as a stick logger. This is stream temperature, intermittence, and conductivity. And so we have a record that's a bit more than a year, not much. And we have basically this logger tells us when water is present, where it's got wet conditions or dry. The red again means that there's dry conditions being observed. And you can see that there was, a couple weeks of flow in the winter of 2020, but otherwise it was dry for almost the entire period. So based on this much shorter record, we classified this reach as ephemeral. The Western Mountains covers, many states in the West, but there's actually two SDAMs that you can use within this region. The method that we're talking about today is what we call the Beta SDAM for the Western Mountains, and it roughly corresponds to the Western Mountains and Coastal Valleys region defined by the Army Corps of Engineers National Wetland Plant List. And it excludes 3 states in the Pacific Northwest: Washington, Oregon, and Idaho. These are covered by the method produced by Tracy Nadeau in 2015. So that method has been in use for quite a bit longer, and within those 3 states, that is the appropriate method to use. But in other parts of the Western Mountains, you use the method we're talking about today. The location of the reach is what you use to determine which SDAM you want to use. It doesn't really matter how much of the contributing catchment or where that's located is. It's really where that reach is located. So if you have a stream here that crosses from Oregon into California, you might use the Pacific Northwest method for the upstream reach and the Western Mountains method for the downstream reach, even if they're close together. When you're talking about streams that are near the boundaries of the Western Mountains, near the arid West or the Great Plains, depending on whether you're on the eastern or western part, you may want to consult the Army Corps' regional supplements on these regions to help you determine if the SDAM for the Western Mountains is appropriate for a site near those regional boundaries. The method was developed following the same process we used for the arid West. We first did a literature review to identify candidate indicators in the technical literature. These were either used in other SDAMs in other parts of the world, or they were well defended and substantiated in the technical literature and the scientific literature. We had 7 geomorphological metrics or indicators. These included things like the frequency of riffles in a reach. We had 8 hydrologic indicators, things like hydric soils. We had 37 biological indicators, things like fish abundance or aquatic invertebrates. And finally, 20 geospatial indicators. These are mostly things related to climate, but also elevation and a number of other characteristics that might relate to stream flow duration. Once we identified candidate indicators, we needed to identify candidate sites, which we either got from the USGS gauge network or were identified in some of the studies that we described, or we talked to local experts. You can see the sites that we ended up sampling in these maps on the right. We ended up collecting data at 149 study reaches, and although we intended for an even distribution of the 3 classes, we ended up with fewer ephemeral and more intermittent sites than we intended, largely because many of the ephemeral, the streams that we thought would be ephemeral turned out to actually be intermittent based on loggers that we deployed at those sites, like I showed you from Calf Creek earlier. We then used a machine learning statistical model to help predict class from these indicators, and then we refined these models to create the final beta method. So why is it a beta method? This is the second method that we're publishing from a series of regional efforts to create regional SDAMs for the entire US. These early methods, the Arid West and the Western Mountains, have smaller data sets than what we're developing for other regions. And so what we wanted to do is put out a method based on the data that we have available, and then have a one-year trial period during which practitioners can provide feedback, but additional data collection can also occur. So if you're interested in contributing to this data collection or the development of this final SDAM, you should contact the Streamflow Duration team at the email address on this slide to find out some more information. So the SDAM for the Western Mountains is based on 8 indicators. 6 of these indicators are actually measured in the field. These include biological indicators, and we have 4 of those. We have the aquatic invertebrate abundance and richness. We have algal cover on the streambed. We have fish abundance, and we have an indicator based on the differences in vegetation between the channel and the surrounding uplands. We also have 2 geomorphological indicators, bankful channel width and sinuosity. And in addition to these field indicators, we have 2 climatic indicators that are measured using GIS, specifically using a web application that we've developed, and I'll be talking more about that later during this training. These climatic indicators include long-term precipitation, as well as long-term mean annual maximum air temperature. So these are both climatic metrics that you determine based on the site location, the reach location, using the web app that we've developed. You do not need to use GIS. You don't need to have access to your own GIS services to use the SDAM. So 3 of these indicators are also used in the Arid West, these biological indicators, aquatic invertebrates, algal cover on the streambed, and fish abundance. The differences in vegetation between the channel and the surrounding uplands, that's not used in the Arid West. However, the Arid West does have a related indicator, the number of hydrophytic plant species. So they have 2 different ways of getting at somewhat similar concepts of how the riparian vegetation is influenced by streamflow duration. The Arid West method doesn't include any geomorphological or climatic indicators. That's unique to the Western Mountains. Another thing that is distinct about the Western Mountains is the influence of snow. So snow persistence affects the way we interpret these indicators. Snow persistence is defined as the percent of days with snow on the ground between January 1st and July 3rd, based on a study from Hammond et al., which showed that this metric had a very strong influence on streamflow duration. And based on these measures of snow persistence, we classified reaches as snow influenced when their average snow persistence was over 25% within a 10-kilometer buffer based on an average of conditions between 2000 and 2019, so basically 20 years of climatic data. So we have the snow-influenced reaches are mostly within those white areas on this map, and the blue areas indicate where snow-influenced reaches are. The snow influence is strongest in the northern and central Rockies, as well as the higher elevations of the Sierra Nevada in California, but it's pretty minimal in California's north coast, the California Sierra Nevada foothills, the mountains of Arizona and New Mexico, as well as scattered portions of Colorado and Montana. Like the climatic indicators, the degree of snow influence is determined using the web application. It's a GIS process where we automatically calculate a buffer around the coordinates you provide and figure out the average So again, you don't need to do any GIS analysis on your own to use the SDAM. Snow persistence affects how these indicators are interpreted. Within snow-influenced areas, we have one set of indicators. We have aquatic invertebrates, the total abundance of them, the abundance and number of perennial indicator families. We look at algae cover. We look at for the presence of fish, bankful channel width, and we look at October precip. When you look at the non-snow influence areas, it's actually it's a longer list of indicators, and they're slightly different in the way they're formulated. I'll just point out, for example, fish presence versus fish abundance. So it does matter where you are. Regardless of whether your reach is snow influenced or not, you want to collect data in the same way. You want to use the same protocol anywhere within the Western Mountains. Once you've collected your data, each of those two strata, they have different statistical models that interpret the data to predict streamflow duration class. Several of the indicators, as you saw on the previous slide, they're used in both strata, for example, aquatic invertebrates, but they're treated differently, whether it's looking at number of mayflies versus all aquatic invertebrates. And some indicators are only used in one stratum, for example, sinuosity. Even though you might not need to use sinuosity in, say, the snow influence stratum, we recommend still measuring it in all indicators at every assessment. And for indicators that aren't used by your model, these can be treated as supplemental information once you're reviewing your assessment. To get your classification, you need to actually run that statistical model. And this, again, might be a challenge for folks who don't know how to use R, but that's why we instead decided to build a web application where users can just input their field data and obtain their classifications automatically. This is the same application that will calculate all the climatic metrics and also determine if your site is snow influenced or not. The web application will run one of the two statistical models to interpret your field data, and it'll result in one of 4 classifications. We have ephemeral, intermittent, and perennial. And we have a 4th category, which is at least intermittent, which means that we've pretty confidently ruled out that the reach is ephemeral, but we're not sure whether it's perennial or intermittent. We don't have high confidence in that determination. I want to point out that the Arid West method had these same 4 classes, plus an additional 5th class known as Need More Information. That classification is not possible with the Western Mountains method. We were able to have higher confidence in all of our classifications. So in the user manual, we have a table like this that helps summarize some of the major differences between the two SDAMs. I'm not going to read this slide to you, but I will highlight a few things. We have more data in the Western Mountains than we have in the Arid West. We implement a stratification approach. We are using a broader array of indicators, both biological, geomorphological, and climatic. The Western Mountains method, you use a random forest model, whereas in the Arid West, you use a classification table that was derived from a random forest model. The two methods both use single indicators. That is, these are indicators that can overrule an ephemeral classification to call something at least intermittent, but the actual indicator varies a little bit. The Western Mountains requires taxonomic identification of invertebrates at the family level, whereas the Arid West only requires order level, but at the same time, it also requires hydrophytic plant species. It requires more or less the same amount of time in the field. And like I mentioned, there's a slight difference in the number of classifications you can get between the two methods.